So we're going to take a look at a couple of parent functions here, new ones for the polynomial chapter, since we've got to get to powers that are bigger than just 2. But rather than say we've got one for degree 3 and degree 4 and degree 5 and degree 6, it turns out that we can lump those into a couple of different things. And so our first one we are going to call odd. We'll start there. Odd whole number power functions. Okay, so we'll look at odd whole number power functions. The basic notation is going to look like x to the n, okay, where n is odd and a whole number. Okay, so x cubed, x to the 5th, x to the 7th, x to the 9th. Technically x to the 1st, although we already know that one and its graph looks a little bit different. So how do we represent this on our arrow diagram? Again, to the nth power, and we have to recognize that if that n is an odd whole number, then there are certain characteristics here. We will do this, in fact, rather than be that general, I'll do a specific example. We'll take a look at cubed. Okay. So this is a place where we want to start talking about the end behavior of the function. So end behavior is asking what is happening way out on the ends of the x-axis. So the negative x-axis when I go out way this direction, or positive x-axis when I go out that direction. Out this direction is where the inputs are going toward negative infinity. That's why I use this notation. Okay. And then we'll grab the points in the middle that capture the behavior of the function. So -1, 0, and 1 are ones that we commonly use there. And then we want to capture the right-hand side of that x-axis as we go way out there toward the idea of positive infinity. Okay. Now, when any negative number to a negative power will come out negative, and that's no different than the idea of infinity either. So this says the outputs, which is our vertical axis, right, this is heading toward negative infinity on the output side. This is negative infinity on the input side. Okay, I'll go ahead and color code this green over on this side so we see that connection. Okay, and then obviously this would be heading toward positive infinity in this direction and toward positive infinity that direction. -1, if I cube -1, or if I take -1 to the 5th or the 7th or the 9th or whatever, it comes out as a -1. 0 times itself 3 times is still 0. 1 times itself 3 times 5 times 7 times 9 times comes out as a 1. And in positive infinity times itself, however many odd times, is going to come out as a positive infinity. Okay. So this gives us a domain. Then we can see domain is from inputs, and their inputs are covered from negative infinity to positive infinity. So we say that the domain here is all real numbers, and the range, we see the range covers the same thing as well, so the range is also all real numbers. If we plot these points that were on there, I'll make some marks here for those. We've got a point at -1, -1, at 0, 0, and 1, 1. Those are the same points that were on our linear function. Okay. But this one has a little bit more unique shape. And I can figure that out if I put other points in here. If I put like a -2 in here, it would get a -8. Right? So a -2 over here would come down more this direction, and a +2 would be up at +8 up there somewhere. And this function, started that out pretty poorly, comes up this way, curves over here, flattens out briefly, and then comes back up like this. Okay. This is the shape of an odd whole number power function. They all look like this. Okay, they will all pass through these 3 points. Okay. As we jump up in the powers, the sides might get steeper, and between -1 and 1, it might wait a little bit longer, closer to the x-axis before it turns and goes over. But this is the recognizable shape of an odd whole number power function. Okay? When we describe the in behavior and what's happening over here, we use this kind of terminology. We would say something like, as x goes toward -infinity, the f of x, in this case, we'll say x cubed, goes toward -infinity. That's giving the general direction of what's happening here. Okay, the farther left I go, the farther down I go. That's what that's saying. On this side, my in behavior is captured by saying as x goes toward +infinity, as I go out to the right, my x cubed goes toward +infinity. I don't know what I'm doing there. So this is basically everything that there is to know about odd whole number power functions. There's not much else that we can do with those. Okay? And if we've got these odd whole number power functions, then we should probably also throw in some information about even whole number power functions. So let's do those as well. Even whole number power function. Which is going to have exactly the same notation, but we have to specify that n is even and a whole number. 2, 4, 6, 8, 10, 12, like that. X squared we already know. We're familiar with what the quadratic looks like. We did this, I would have introduced this via Desmos activity when we did that. Okay. But x squared certainly applies to this, but it turns out that x to the 4th and x to the 6th and x to the 8th look a lot the same. Okay. So let's see if I can get this box to disappear. Doesn't look like I'm going to have much luck with that today. Oh well. All right, so we'll grab a sample in here. Since we already know x squared so well, let's go ahead and we'll say it's x to the 4th. Okay. And we're going to be interested in what's happening with the on the left-hand side again. And -1, 0, and 1 are very revealing points for these. And then what's on the positive side of the x-axis way off to the right. Okay. And when we say to the 4th power, it means that we're multiplying by itself 4 times. And if you take negative numbers and you multiply them by themselves an even number of times, every pair of them ends up being positive. And so this actually ends up being positive on that side. And it's also positive on this side. Okay. -1 times itself 4 times is a 1. That's an example of that negative thing going on there. 0 times itself 4 times is, or 6 times or 8 times is also 0, and the 1 becomes a 1. So we can see on this one again that the domain is going to be all real numbers. It goes from -infinity to infinity, but on the range side here, when we're talking about the range, I can't get any negative numbers out. Okay, I can get as small a number as 0. 0 is as close to being negative as I can get without being negative. And I can go all the way up to positive infinity. So I describe this range as y greater than or equal to 0. So let's put some points down. We've got these points at -1, 1, 0, 0, and 1, 1. And this is going to, I mean, these are the same place that these fell in for our parabola. Okay? The shape of a degree 4 is sometimes called a quartic. parabola. Okay, this is not, if it's x squared, it's a parabola. Anything else is not technically a parabola. But it looks very much the same. As the powers get bigger, the sides get steeper, and the bottom gets flatter. Okay, so maybe not as well represented on the bottom there as it was meant to be. Okay, again, this is negative infinity out that direction on the inputs. This is outputs or inputs of positive infinity, and my output in this direction of positive infinity, this would be an output of negative infinity, which actually doesn't come into play in this problem. So my description of the end behavior, I would say as x heads towards negative infinity, x to the fourth here heads toward positive infinity. And as x heads toward positive infinity, x to the fourth heads towards positive infinity. Okay? This is our starting point, what we need to know about even whole numbers. On the previous slide, what we need to know about odd whole number power functions. We will be talking more about that as we go through this unit.